we're going to start taking a look at an example of how we can use these Newton-Cotes formulas to be able to approximate an integral to determine whether or not it's actually a good approximation or not. So we have a scenario where we have a catenary modeled by a function. We have this 300 cosh of x over 2000 minus 280. X is between -2 and +2000. And you might remember from integral calculus, this formula where we can find the length of a function, 1 plus the derivative of the function squared, and integrate it from b to a, or a to b. Now, let's use a numerical method because this might be fairly difficult for us to be able to integrate the derivative of this thing and then take the square root. In fact, it might be virtually impossible. Somebody was nice enough to be able to give us the exact value, or at least close to the exact value, is going to be 4,018.221769 feet. And so we're going to first of all create a plot of the above function to kind of see what we're getting to. Then we're going to use all 5 of those rules that we looked at before. All right, so all 5 of these animals to be able to approximate the value of the length. And then we're going to find the percent error as well. And then finally, what we're going to do is we are going to use the results and put them into a table. So we're going to have trapezoidal, Simpson's 1/3, Simpson's 3/8, Boole's rule, set 6-point, all that stuff. And we are going to see whether or not that if we increase the degree of the polynomial, then we get a better interpretation, which we should. Right. So first thing first, let's go ahead and get our MATLAB going. And in MATLAB, what we're going to do is we're going to start by defining a number of things. All right, so first things first, let's get some sims variables because we do have to graph this. So I'm going to say sims, I'm going to have x, y, and then I'm going to have a function f. All right, and my function f, I'm just going to make that the original function, which was 300 times the cosh of x over 2000 minus 280. All right, so that's our function that we're looking at. And let's just do an easy plot of f. Okay. Really easy, really nice and easy function. We're going to run it. And it's the first time I've run MATLAB today, so be patient as it runs through for us. And we should get that catenary sort of relationship where it's like almost parabolic, all right, but it's really called a catenary. So, oh boy, MATLAB's really taking its time. Well, while MATLAB is taking its time, let's start doing some of the other parts. And let's start by defining our actual, right? And our actual, if you recall, was going to be equal to this value. Okay, so 4018.221769. So, oh, finally, it looks like the figure's coming up. So here is our catenary. All right, so it looks like it only went from -6 to 6, so we could certainly change that from -2000 to 2000. All right, so we'll run it again. Hopefully this time it's a lot faster. And while that's running, invalid expression. So we could just keep it at the original. So I'm pretty sure easy plot. Maybe I don't need the brackets. Nope. So maybe I do need the brackets in there. Let's try one last time. Oh, that's why. Duh. I had that actual in there. Let's try one last time, see if easy plot gives it. Okay, so we do have the catenary, and it looks like the highest point it gets to in that range is about 180, all right, whether that's meters or feet or whatever. So at least we have a good idea of what we're looking for at this point. All right, so now we have an actual, and the actual value is going to be that 4,000, and I know I've been trying to get to it for a while, 4,018.221769. And now this isn't really the function that we're looking at, okay? So now we do have our lower and our upper bounds. The function that we're really looking at is the arc length, okay? So we're going to redefine f in a moment, all right? But a is going to be equal to -2000, and b is going to be equal to 2000. And now I'm going to redefine the function. And I'm going to let f now be equal to the square root of 1 plus the derivative. And you might remember to find the derivative, you say diff, we're going to differentiate f with respect to x, and we're going to square that derivative. Okay, so what we're doing here is we're just finding the arc length. All right, and this function is going to represent our arc length, okay, or at least that's what we're going to integrate. All right, now check this out. If I try to integrate f with respect to x from minus 2000 to 2000, all right, and I'm going to uncover the square root or this length function. Let's check out what happens if I try to execute this. All right, so this is our function, and MATLAB cannot get an analytic value for this. Okay, so it says I don't know how to integrate that because there is no antiderivative for this. All right, so the only way to be able to figure out what the length of the catenary is going to be is to utilize these different numerical methods. All right, so I'm going to get rid of this int because we don't need it. Let's start by programming the trapezoidal, and I'm going to say the trap. I'm just going to call it trap, and just to make sure you understand where we're getting this from, trap is coming right from here. Okay, so it's going to be b minus a f at x naught plus f at x1 divided by 2. All right, and in this case, x naught is a, x1 is b. All right, so it should be really easy to program this. So trap is going to be equal to b minus a times, and I'm going to do a subs. I'm going to do chase times subs, and I'm going to substitute back into f. I'm going to substitute the old value as x and the new value is b. All right, and we're going to say the exact same thing, except now we're going to have a, and we're going to divide by 2. All right, now I'm just going to leave this open. All right, and we know what the actual value is. It's 4018.2217. Let's run it, see if we get anything even close to that. Of course, it doesn't help. Let's do an f print f, and I'm just literally going to do %f because that's the only thing that's going to be output, and /n. All right, so let's try one last time, and it would be helpful if I told it to print out trap. All right, and so here is our, with just the linear approximation, 4061. Now, I know 61 and 18 are fairly far apart, but when you start getting to the 4000s, it's not negligible, but at the same time, it's a reasonably decent estimate just for a linear approximation. So it looks like this formula is okay. Let's get the percent error. Okay, so I'm going to call this T error, and it just seems appropriate in math that we have terror, ha ha ha. That's going to be equal to the absolute value of our trap minus the actual, and we're going to divide that by actual. All right, and we're going to multiply it by 100%. All right, now I'm going to leave that uncovered, and I'm going to, this time I'm just going to print the T error or terror, and let's print that out. And even though we're fairly far off in our minds, we only get about a 1% error. That's not too awful for a linear approximation. Now, of course, we want more than that. All right. What we want is we want to go through and we want to get the 1/3 and the 3/8. All right. So we're going to go through those. And so the next one I'm going to call is, let's just call it the sim13. So sim13. And if you look at our formula, I'll bring the formula back up. That's going to be equal to x naught for x1, which is basically the midpoint, right? So remember in our last video, x1 was just the midpoint between a and b. And so here's what we're going to do. We're going to have our b minus a, just like we had before. And we're going to multiply that. We still have subs a and subs b, all right? But the only thing we're going to do is we're just going to add in 4 times the sub of f with respect, or f and x. And what are we going to sub in? We're going to substitute in b minus a over 2, the midpoint. And we're going to divide all of that by 6. All right. Now, once again, what I'm going to do is I'm just going to do an f print f and %f, and I'm going to call our simp13. Just to show you that if we were to execute this, all right, now we get 4061, all right, and that's pretty close again to what we were looking at before, all right. Not too far off, not too much better, but if we were to go ahead and say this is our error, I'm going to call it S13 error is going to be equal to, we could just do the exact same thing here. And I'm going to call it simp13. All right. And let's just take this guy, move it down, suppress this, and I'm going to call S13 error. All right. So now we're getting about a 1.08 error. Okay, so not too much different than the first one that we had. So we're hoping as we go along, these start to get a little bit better. All right. In fact, I think what we should do is a plus b minus a over 2, right? Because this just gives us, let's give that a shot, because this is going to tell us how far to move. Ah, that's a lot better, isn't it? All right. So whenever you're doing this, make sure you have that a plus, because this tells you how far that you have to move each time to be able to get to the next value. All right. So this is just basically what h is, right? But you have to add that to a. All right. Now, we're going to do this again and again and again, but check this out. I'm going to call this simp38. All right. And if you look at our formulas, check this out. There's a pattern that's going on here, as there are with a lot of numerical methods. We have b minus a over 8. We already have b minus a. We have x naught. We have x3. All right. But now what we're going to do is we're just going to increment in thirds. All right. So check this out. We're going to keep the exact same thing. We're going to have the first one, and we're going to have 3 subs of a plus b minus a over 3. Now I'm going to copy this, and I'm going to have 3 subs b minus or f at a plus 2 b minus a. All right, so this is going to be the subs at, I guess technically we should just have this at a, and then this is b, just to make it a little bit easier for us to understand. All right, so we're starting at a, and then what we're doing is we're just going up by a third. All right, so we're adding a third of the step size, or the step size, which is going to be a third of the distance between B and A. And then we're adding 2/3 of the distance between B and A. And then this is going to be our final point B. All right. And the last thing we do, I think, was we divide by 8. All right. So hopefully you're starting to see the pattern with this. All right. So we're going to divide by 8. Is that when we change this, right, and I'm going to just call this S38 error. All right, and you're going to see that this actually is going to be a pretty good error, or a pretty small error out of this. All right, so let's run this, and there we go. All right, so that's really nice. So now we're getting even smaller error each time. All right. Now I'm going to call this one bool. All right, so I'm just copying this. I'm going to get rid of these f print f's because we don't need them anymore. Let's call this bool. And bool is going to be equal to, now it's going to change a little bit for bool's rule. So for bool, notice that we have a 7, 32, 12, 32, 7 pattern. All right, so the coefficients, it doesn't necessarily, it still follows a symmetric pattern, but it's just the numbers that aren't necessarily ones that we would think of off the top of our head. All right, so we're going to have 7. All right, and we're going to have our 32. All right, and again, we get that right from here. So we have 732. And now what I'm going to do is I'm going to change this to b minus a over 4. Now I'm going to have the 12, right? Because in our formula, we have 732, 12, right? I'm going to change this to 2 over 4. Right? And I'm going to copy this, and this is going to be, we're going to get back to our 32. This is going to be subs 3, 4, and then finally 7. All right. Now the last thing we have to do is we have to change the denominator, right? So this is going to be divided by 90. All right. So be careful. Make sure you change everything as you're going along with this. I'm going to just change this to B error, and I'll call this bool. All right. So, and check this out. Now we're down even smaller. Oh, I need to change this to bool. So now we're down to, let's try one last time. Although you can see that this is almost the exact value anyway, right? So if you're looking at this as, now it's accurate to the tenths place, but our percent error is now even lower than what it was before, right? Now let's just do this one as our 6 point. So I'm going to say, I'm going to call this 0.6. Don't start it with a number, by the way. MATLAB doesn't like that. And our pattern is going to be 19, 75, 50, and then 50, 75, 19. So 19, 75, 50. So this is our 19. And then we're going to have 75. And this is going to become over 5. And we have 50. All right. And this is going to be 2 over 5. And then we're going to have another 50 right here. And we're going to change this to 3/5. I'm going to copy this one. And we're going to have a 75. And we're going to change this to 4/5. Right. And then finally, we have a, I think the first one was 19. Yep. So we're going to change this to 19. And the denominator should be 288. Right. I'm going to call this 0.6 error. I'm just going to call it P6 error. And let's just call this P6 error. All right. So hopefully I didn't make any typos in this. I'm going to run it. All right. And I forgot to change this to P0.6. That would be helpful. All right. And an even smaller error. All right. So the good news is, as each time we increase the order of the polynomial, we get a better approximation for this. All right. The last thing that we have to do is we have to actually make a table out of this. So we're going to have our fprintf, and we are going to have the rule, so the name of the rule, and then we're going to have the approximation, and then we are going to have the percent error. And this is the easy part. And so we're going to fprintf, we're going to have trapezoidal, and we're going to have a %f and a %f. Right? And /n, and we are going to call trap and terror. Right? And I'm just going to copy this, and we're just going to go right down the line. All right, so this is this was our trap, and this is going to be our simp 1/3, and we called this simp 1/3. And we're going to call this guy S13 error. Right. And then here we have simp 1/8, or simp 3/8, excuse me. And let's jump this over just a little bit. This is going to be our simp 3/8. And this is going to be our S38 error. And then we have our bool. And this is going to be bool and B error. And then I think the last one is the 0.6. All right, so this is going to be our 0.6 or 6 point. All right, and this was 0.6. And this was P6 error, I believe. All right, so I went through that kind of fast. Hopefully I didn't make any errors. We don't need this anymore, so let's go ahead and execute and see what we get. All right, so we're going to run it. All right, and check this out. Each time we're getting really close to that actual value, and the actual is 0.221769, so we're getting closer. Obviously, if we just had a few more degrees on our polynomial, we'd be able to get even better approximation. All right, so just running that out, just too many there. Let's try one last time. Of course, I'm going to try to set it up so that it looks really nice and lined up. So really cool that we can use these rules for integration to be able to approximate our definite integrals without necessarily partitioning in it too difficult. All right, so the next thing we're going to start looking at is we're going to start looking at these things that we might have seen in our integral calculus course. So hang tight, we're going to take a look and see how we can program those types of algorithms.